Alright, so this is the second page of our polynomials test review. We're asked to write the equation of each function. So these are some polynomial functions, and what I have to be able to identify is the type of function and its parent. So right here I see this first function, and I can quickly identify it as a cubic. I know it's a cubic because I've got this little point in the middle here where the graph, it's not exactly a turn, but I go from the graph is kind of cupped downwards to here it's kind of cupped going up. This point's called an inflection point. You'll learn if you study enough math. But this is definitely a cubic. I know because of that weird little wiggle in the middle. So its parent is y equals x cubed. So what I need to think about here is how to transform this parent graph, which I've already sketched, to get this. So I know that my parent cubic goes through the origin. The other points on it, if I cube 1, I get 1. If I cube -1, I get -1. So I get, again, this kind of wiggly graph. And I can see over here I've gone, appears like I've gone 5 to the right and 2 down. Now I can check, clearly there is no reflection, and you can check this also has these points that are spaced out one by one. So there's no stretch or compression either. Though that is something we probably won't deal with, identifying a stretch or compression from a graph anytime soon. So if I'm going 5 right and 2 down, the equation here of this function, well, it needs to be an equation, it needs to be a function. I can say y equals or maybe f of x equals. Since there's no reflection or stretch or compression, I can just go right in and say x. To go 5 to the right, I'll say -5 cube, because it's a cubic. And to go 2 down, I will have -2. Now how about this other one to the right here? Well, I look at this, and it looks sort of like a parabola in some ways, but I notice how flat it is up here near this point, near this vertex. That flatness indicates that this is, in fact, a quartic. That's something that happens in a quartic, not in a quadratic. The other thing I could tell is, again, looking at the points, I go out 1 and down 1, indicating that this has actually been reflected. But a quadratic, I would go normally out 1 and up 1 on both sides, out 2 and up 4, because 2 squared is 4. Whereas with a quartic, as I go out 2 from the vertex, I should expect to be 16 points, either up or in this case down. So what I see is this goes down very fast. It's more U-shaped than a quadratic, which is more of a gentle curve. So what can I see here? It's flat, so it's a quartic. My parent is y equals x to the 4th. What transformations do I have? Well, again, it's oriented downwards, thinking about the end behavior. So that means I have a reflection in the x-axis. And again, if I'm looking at the vertex, going from the origin to there, I've gone 1 right and 4 up. So I need to put this into my function. And again, I can say y equals or f of x or g of x if that suits me. To reflect, I put a negative in front. To go 1 to the right, I'll have x minus 1. It's to the 4th, so that it's a quartic. And to go 4 up, I just add 4 onto this function. Okay. Excuse me. How can I write an equation for a quartic function that has the following transformations? I need a vertical stretch by a factor of 5/2, and I have translations going left 10 and up 3. So again, it's a function. I can say y equals f of x equals g of x equals. It really doesn't matter. I will say f of x equals because I already started writing that. To be stretched by 5/2, I'll plop that down in front. To go to the left 10, we remember inside, going left and right, the signs behave opposite of how our brain wants them to. So left 10 is actually x plus 10. It is a quartic. So quartic would be a 4th power. A cubic is a 3rd power. Going back to last unit, a quadratic would be a square right here, and a 2. And to go up 3, I will add 3. Zoom out a little bit. There we go. So That's a little look at how parent functions for these two basic polynomials work. Now the next topic that's on here is multiplicity. Let's remind ourselves how multiplicity works. Now we'll talk about how to find multiplicity when we deal directly with this, but let's remember what multiplicity's effect on graphing is. If I have a root whose multiplicity is 1, 2, or 3, I can predict pretty well what the graph looks like near that point. If the multiplicity is 1, the graph will cross straight through the axis. If the multiplicity is 2, I will touch the axis without actually passing through. And if the multiplicity is 3, I will sort of wiggle through, where the graph gets basically horizontal for a moment. I still go through, but I go through with this weird little wiggle, like a cubic. Now you see here I drew some other turns and stuff to make them look more like polynomials, but I was focused only on the zeros and the multiplicities, the behavior those multiplicities would show me. If I wanted to sketch the graph of a function from factored form, I could take all these multiplicities, piece them together with end behavior. And that was what we talked about when we taught this lesson. Let's see what we're being asked right now. What are the roots and multiplicities for this function? I'm going to make a little table, if my pen is going to cooperate. There we go. Now remember, root, 0, solution all mean about the same thing as x-intercept. Little differences of context. I see 4 factors right here. They are 2, x plus 5, 3x minus 1, and x minus 4. And I set these equal to 0 and solve. 2 does not equal 0. This is an equation with no solution. If x plus 5 equals 0, x equals negative 5. If x minus 4 equals 0, x equals 4. And be careful here. I'm sure you can solve this pretty quickly, but don't be afraid to write the work. 3x equals 1, divide by 3, and x is 1/3. So I can see I have 3 roots, namely negative 5, 1/3, and 4. And I'm asked to identify the multiplicity of each of these roots. So if I have a root, negative 5 for instance, negative 5 comes from the factor x plus 5. X plus 5 is raised to the first power. So that power, that exponent, tells us the multiplicity. The root negative 5 has multiplicity 1. The root 1/3 has multiplicity 2. And the root 4 has multiplicity 3. Now again, we drew this a minute ago. We could make a sketch of this function to actually show these multiplicities. At 1, I would cross the x-axis. At 2, I would touch the x-axis but not go through it. And at 3, I would wiggle through the x-axis. So we're asked, at what points will the graph of g of x go through the x-axis? And we can answer that it goes through at negative 5, 0, because it did say points, and 4, 0. Let's do one more problem involving multiplicity. Here I have a function, its graph is given to me, and I want to identify the zeros, the factors that they must indicate, and the multiplicities that the graph tells me. So if I look right here, my zeros are negative 3 and 0 and 4. Now remember we learned the factor theorem, which stated that if I have a root r, then I have the factor x minus r. So for each of these, x minus negative 3 is actually x plus 3 is the factor I would have. X minus 0 is just x. And x minus 4 is, most obviously, x minus 4. What about the multiplicities? Well, looking at the graph at each of these points, I cross the x-axis, and at 4 I touch the x-axis. which would indicate to me the multiplicities are 1, 1, and 2. How can I use this to find the minimum possible degree of this polynomial? Well, we talked previously about using the number of x-intercepts and the number of turns to predict. Using the multiplicity can give us even more information. I can just add up these multiplicities, and that gives me another estimate of the minimum. That gives me another idea of the minimum possible degree. Not necessarily an estimate. You have a very complicated problem, that'd be one thing, but let's leave that issue to another day. 1 plus 1 plus 2, the minimum possible degree of this polynomial is 4. Now lastly, we are asked about the sign of the leading coefficient. Well, I look at the ends, the end behavior. This graph is generally going down. In particular, for large x's, as x approaches infinity, the graph is falling. That tells me that this must indeed have a negative leading coefficient, because the graph generally goes down. And there you have your answer.